I've distinguished in the previous section 3 kinds of observations, and now I'll use these distinctions in order to argue that at least some observations are theory dependent. That is, they require theory in order to make theoretical assumptions in order to make and justify these observations. Why is theory dependence important? Well, it's important because it complicates a very prominent but probably false view about empiricism, or a version of empiricism. And that's the following. It's a sort of early 20th century philosophy of science that had a substantial influence on the sciences, in particular on modern physics, called logical empiricism. So their idea was that we can separate out observations and theory, so that we have a separate realm where we're making observations, or we're describing observations with the help of what they call observational sentences, but they're sort of pure observations. And then we have that as a sort of as a separate body of knowledge. And from that separate body of knowledge, we can then go and justify, or build and justify our theories. And that's, of course, very convenient, right? Then you have a clear foundation on which all theories are built. And when in doubt whether a theory is justified, you just have to look up in the set of observations whether there is sufficient evidence for that theory to be justified. Well, that sounds very nice, but theory dependence makes things more complicated. And now I want to argue for this theory dependence in the following way. First of all, let's look at indirect observation. And here you already suggested that, well, it seems that there's a close connection between this idea of indirect observation and the role of theory in it. And if you look back to the bubble chamber example, it's clear that if we want to say and want to justify that we actually observe subatomic particles in these bubble chamber trails, then we need to make certain theoretical assumptions. We need to argue that, well, there is a theoretical connection between these trails and the particles that cause them. So we have to make assumptions about the properties of the liquid in a superheated state, about the relation between particles and ionization, and then also about the sort of relationship between the particle energy and the size of the bubbles. So without making those assumptions, it is entirely unjustified to point to bubble chamber trails and say, I see particles. So it is required that you have such a relation between the property or event of interest and the observable property. And that relationship is one that it must be justified with some regularity. So saying that, well, always, or at least most of the time, with a sufficient probability, charged particles sent through a bubble chamber produce these trails, and nothing else does. And then, of course, you would further unpack this. So we can say that indirect observation is always theory dependent in this way. We cannot make these observations. We cannot say that we have observed something without that theory being true, or without us believing and being justified in our beliefs that this theory is true, or this model is true. Okay, so that's one. But now I want to also argue that even aided direct observation requires theory, at least sometimes. And for this, let me give you a historical example of Galileo Galilei observing the 4 moons of Jupiter. This is, of course, one of the great moments in the history of science, and many times this moment has been described as basically a sort of a stubborn science and intellectual establishment that refused to even consider Galileo's evidence. And the evidence in that narrative is described as inescapable. So, for example, in Bertolt Brecht's play Galileo, there is the Cardinal Bellarmine of the Inquisition, and he says, in the play at least, we don't know what he really said, but in the play he says to Galileo, I could look through your telescope, but I don't need to. And the implication is that, well, if he only looked, then he would be convinced, right? Then he would see the evidence, and then there would be no question anymore. But because he refused to look, and he sort of insisted that he already knew by studying Aristotle, and of course insisting on the church fathers, that then that's why he could retain his belief in the geocentric model. But here's a report of someone who was there when Galileo made his first rounds amongst the scientists. Now, not necessarily the defenders of the old order, and how difficult it actually was. I'll read it out because I think it's really nice. So it says, this is in a letter from someone who was there at the time to Kepler. It says, Galileo Galilei, the mathematician of Padua, came to us in Bologna, and he brought with him that spyglass through which he sees 4 fictitious planets. That's the 4 moons of Jupiter that were so crucial in the development of the heliocentric model. On Earth, this spyglass works miracles. In the heavens, it deceives. Because other fixed stars appear double. I have as witnesses most excellent men and most noble doctors, all acknowledge that the instrument deceived. And Galileo became silent, and on the 26th, a Monday, dejected, he took his leave from Mr. Maggini very early in the morning. So the report here of an eyewitness of this use of this new instrument for aided direct observation tells us that contrary to the narrative of it only required looking through the telescope, that it didn't work. And it was that even that intellectual scientists at the time, they were not convinced. Why was that? How is this possible? Well, the telescope exhibits optical aberrations. And on Earth, looking at other objects with the telescope, you can distinguish, right? You can actually go and directly, unaidedly observe a certain object. Then you walk away a certain distance, and you observe it through the telescope, and you see, so it actually shows the object as it is. However, there are also certain sort of blurrings or something like that that happen maybe on the rim of the vision field, the aberrations. But now you train your telescope to a distant star, and of course you can't observe that star directly, but you can you see that things are blurred, and sometimes it seems that they seem to be appearing double. So there seem to be all kinds of effects that the telescope makes that you question whether it actually depicts the stars that in the heavens in the right way, and you can't really check. So it is uncertain at least for Galileo's contemporaries, whether this new instrument actually produces apparent experiences that really don't correlate to any real object, and therefore they're rejected, at least in this initial encounter. So what do you need in order to counter this argument? Well, you need a theory of optics. You need to explain why optical aberrations occur, and how you can sort of divide these aberrations from the depiction of the actual phenomena that are amplified by the telescope. Now, clearly, this doesn't apply to all aided observations, because in many cases you'll be able to compare what you see in through the instrument with the seeing actual. Looking at things directly. This is why on Earth it works, right? This is why they report that they find the telescope useful, but not for the purpose of looking at stars. So of course, it's exactly where these aiding instruments should help that the question arises, and where do they actually help, or do they deceive in those domains? And for that, again, you need theory, which Galileo didn't have. So, at least in some cases, even for aided direct observation, you require theory. And that makes both indirect and aided direct observation theory-dependent in this sense. If that's the case, if observation, not always, but often, certain types of observations are theory-dependent, then something's wrong with this picture. Now, we can't have observation as the foundation of theory, because now observation already relies on theory. So instead of having sort of one thing built on the other, you have something like a circle. Now you'll need to, and circle in the first place doesn't look so good, right? So there's the issue of circularity. And in fact, this is one of the most interesting methodological and philosophical problems. How do people get around the problem of making observations that are supposed to support theory if the observations already require theory? Here's the example of temperature measurement, which was a huge thing in the 18th and 19th century. Developing reliable measurement instruments for measuring temperature. Temperature, of course, at least in the sense that we want to measure numerical temperature, will be indirect. So we don't have access to kinetic energy, and if we want to numerically pick up on that information, then we need to have an indirect, make an indirect observation. Now, one way, typical way that was proposed in the 18th century and has been dominant for quite a while, is to construct measurement instruments for temperature by relinking temperature to density of liquids. And the way how these thermometers are typically constructed is the so-called two-point method. So you have two particular points, typically boiling and freezing point of water, and then you assign, let's say, the point A, the point C and the point D as those 2 points. Note here, this is the old thermometer that Celsius used, so he still had the numbers inverted, 100 for freezing and 0 for boiling. And then you just, in equidistant steps, you divide the scale. So you write from 100 to 75 to 50 to 25 and so on. Equal distance, and you say, well, as the liquid expands, it rises in the glass column, and therefore we are assigning different numbers. Well, that requires that there's a linear relationship between temperature change and density change. How do you know this? Well, this is a theoretical assumption. What evidence would you have for such a theoretical assumption? Well, temperature measurement. But that, or at least experiments involving temperature measurement, but that's exactly what you're trying to figure out, right? So you can't separate these two issues entirely. And the 19th century scientists were faced with the formidable problem that different liquids expanded differently. So here are 3 examples. So some of the main contenders were water, alcohol, mercury, and air. So what did people do? Well, they faced the problem of, so the so-called problem of gnomic measurement. That is the circularity problem that I've illustrated. Now, may want to go a little bit into more detail. So we want to measure a particular quantity x. We can't directly observe quantity x, but then we have some quantity y that is directly observable. So now we're sort of thinking about setting up an indirect observation procedure. But in order to do so, we need to rely on some regularity that relates x and y in the right way. And the form of this function, the form of this relationship, that's what we don't know. We can only find out about this by actually applying a measurement of x, which we don't have, because that's what we started out with. So here we had that is a more general formulation of the circularity problem. Well, that seems pretty formidable, but in the 19th century, people found solutions to it. Let's see whether you find these convincing. So in particular, the French scientist Regnault, he proposed to avoid discussing theory altogether. He was, of course, aware of the problem of gnomic measurement, that he required some underlying empirical regularity, but he wasn't out to find that. But instead, he was trying to show that certain kinds of thermometers were generated more consistent measurements than others. So there were, by minute variations in the respective setup of the temperature measurement, he showed that some thermometers filled with some liquids varied enormously, while others varied a lot less. And interestingly, he was rather critical of the mercury thermometer. So he compared the mercury thermometers that were set up with different kinds of glass, including Swedish glass. And he showed that in comparison to the measurements of the air thermometer, these different mercury thermometers showed substantially different readings. Now he compared different air thermometers. What do you mean by different here? Here, what he varied is the initial pressure in the respective vials. And what he found is that in contrast to the large variations in mercury, the variations here were actually very small. That was his argument why the air thermometer was better than the mercury thermometer, because it yielded more consistent, more comparable results. And by that he aimed to avoid the circularity problem that would seem to require identifying these irregularities or laws behind the measurement. Okay, so to summarize, now argued that indirect observation is always theory dependent, while aided direct observation is sometimes theory dependent. That is, I think, an interesting finding, even though it is not universal. And I've argued that theory dependence complicates empiricism. We can't now go with the simple foundationalist issue, the foundationalist picture, yet, because we cannot go with this simple foundationalist picture, we are facing a circularity problem, and I've given you an example of how this can be solved, but that might not be the only one.